All right. Well, welcome everybody. We're now sort of back to spring. So good that everyone got some folks in the classroom, some folks online. Let me just recoup some of the announcements that have been going out. And this one just came in this morning. One of our students sent me this link. That has a list of some really interesting data sets. So for the data science class, it's good, you got to start your project early. And if you're having trouble coming up with an idea, one way to start is to look at some interesting data sets and then think about, what are some questions that I could ask about those data sets? So that may be an idea for a project. And some other things that I should mention here is, let me just, we have some inclement weather. Yes, another one is coming up tomorrow, and that one I am going to try to also do it as a Zoom meeting. But we have a group from Windstream that is going to be coming out to campus tomorrow. And for folks who can come to campus, we're going to have pizza and beverage so that during the lunch hour, you don't have to be hungry listening to the presentation. Folks can get some pizza first. And then these are the topics that the folks at Windstream are going to talk about. And in particular, they're going to be talking about the technologies and platforms that they're using to develop their AI applications. Again, I really encourage you to come out and check out this event. One of the things you can do for your data science project is, maybe you want to pick one of the tools or platforms that they say they're using and see if you can develop a small project out of it. I was going to say, this is a great way to sort of connect what you're doing in this class to a potential career path. Many of these AI tools have a free tier, and many of these AI tools have a ton of documentation out on YouTube and out on the web. And so you could, give yourself a little challenge. Again, I want to, see if I can, come up with an AI tool that will, recommend, I don't know, things to eat or movies to see or things to do, or what to wear tomorrow, or something like that. You can kind of give it a little challenge, and again, see how you could build some rudimentary prototype. And again, part of the data science project is writing about your experiences, what worked, what did not work, and what were the challenges. And this is a great sort of first step. And we had kind of a nice discussion going on before class. If you're a PhD student and you're looking for, I'm as a PhD student, I'm supposed to come up with research ideas because I've got to be able to let faculty know here's where I want to make a contribution. A lot of that starts off just reviewing and seeing what folks are doing and where they're having problems. So that may be a source of inspiration and get you some ideas. This has been a busy a week. On Thursday, again, if you're on campus, we've got a Titans of Industry. This will be a panel discussion. And again, we're going to have several, sort of top industry leaders, giving a talk. And part of what they'll be talking about is how AI is transforming how they do work. So again, that one is going to be right after this class, 3 p.m., right down at the EIT auditorium. And then again, they're going to have a reception at the Bailey Alumni and Friends Center. So again, snacks, nothing like, food to go with the event. And then one final thing is just I'm reminding students to keep an eye on your email. Now, for students who are graduating this spring or this summer, you don't have to pay attention. But for students who are planning to register for classes for the fall, we are moving to a new registration system called Workday Student. And so keep an eye on your email for training, for instructions, and they're going to have some nice events for March 5th from 10 a.m. to 3 p.m. You can come by the Ottenheimer Library 10 a.m. to 3 p.m. and they're going to be doing hands-on demonstrations, activities. Again, I think snacks will be provided, so definitely keep your eye out for that. Okay, and then that's the main thing that I had on my to-do list. Just remember that in terms of assignments, I think it's fine to move ahead with the text analytics, and then Dr. Dagtas had put together a very nice set of image challenges. And that's under the image challenge assignment where he's given sort of 3 different mini projects. And just like we let you choose from a choice of tutorials, students can choose from a choice of different projects. And this in particular, this first one is a very nice starter project. If you're going to work with images, what we found is, all of the data requires pre-processing. If you're going to work with statistics, you have a spreadsheet, you got to clean up the data before you analyze it. If you've got text, there's all sorts of pre-processing that you have to do to get the text in a format that you can then analyze it. And images are no different. So there are some basic functions like taking a colored image and converting it to black and white, or taking an image and sort of blurring out some of the details so the main features stand out, or being able to eliminate anything that isn't a strong enough feature, or being able to do edge detection. These are all things that are typically what folks will spend a lot of time on before they can feed their images into, for example, a convolutional neural network. So what you'll do for this type of assignment is start off with a colored image. This could be something you take on your phone, could be a selfie, you take a picture of whatever you want. And then this is kind of like a scavenger hunt. What you want to do is go out on the internet and just kind of Google, how do I turn a colored image into black and white? And what you're going to do for this assignment is say, here's my starting image, and here's where I found some code, and then I went into Google Colab and I ran the code against my image, and here's the code, and here's what my output looked like. And that's the main gist of this assignment. It's just giving you practice saying, yeah, I want to know how to do something. I want to know a little bit more about what I'm doing. Let me go out on the internet, do some Google, find some code, or find a technique or a tool. And what this assignment is about is simply for those 4 challenges, saying, here's where I started, here's the technique that I applied, here's the end result. And Dr. Dagtas, this is a good segue because in today's, he is going to talk to you about, and here, maybe we'll just go right here. And I will also, let me move this right here. And I'll do the same thing in case we're I may turn off the video just to make sure. And I was going to say, second, here we go. Yeah. Yeah, we can make it, yeah, as big as you'd like. Yeah.
Looks good.
Yeah. And yeah, we'll let you just tell us a little bit about imaging, processing, and retrieval.
All right. Thank you, Dr. Pierce. You're welcome again to our more in-person session this time. So last week on Tuesday and Thursday, mostly remotely, we went through some introductory material, some aspects of multimedia databases, data science applications, as well as information systems. So within that context, we looked at what typical so-called multimedia data types might be. This week, we're going to be a bit more technical, get into some of the details of how to handle these data types, starting with images today. And on Thursday, we're going to continue with some discussion on audio processing. And when images and audio come together, you can imagine what comes next. Also, video data itself has its own challenges. So it's video, it's not just images combined, obviously. The dynamics and temporal dimension and interrelationships, multiple tracks, the idea of including the dynamic or changing aspects and motion, etc., comes into the so-called picture, so as to say, or to the video, right? But today we're going to look at the images a bit more closely, starting with the representation of images in some ways and some basic processing techniques in relation to also to the project that Dr. Pierce has discussed briefly. That's going to be sort of an implementation or application of some of the ideas that we're going to be discussing today. And the two other projects, one of them is on multimodal processing, one of them is on video processing. Will also be implementations or applications of what we'll be discussing today and or on Thursday. So at the end of the class Thursday, you will be in a better position to both understand the basics of what is involved in these in processing of these basic media types, and to be able to attend one of the projects that have been mentioned. So we're going to discuss this in a little bit more detail, but let's start with the history of digital images. I was also surprised to find out that the history of the digital images actually dates back to more than 100 years ago. So in 1920s, people already actually obtained some digital image. These are two of those early examples. So these were not on film. These were actually represented with electrical signals. And as you can imagine, in this class and in the context of any information systems, database, etc., when we refer to images, we're not talking about the old, as we discussed last time, the analog representation on film or on a piece of paper, etc., but the digital representation, which will be basically some binary representation. So we will begin with some of these basics on how images can be represented. As we know, in two-dimensional space, at least, an image is a matrix of values, right? A two-dimensional set of values. You have X and Y dimensions typically, and this is obtained for real world images by digitizing, capturing and digitizing the optical signals of the environment. But what are the contexts in which digital images can be used? So we discussed this briefly last time. Images versus graphics. Images is what you capture from the real world, so this is a collection of pixels for that reason. But graphics is the representation of synthesized images, computer-generated imagery. And so this is about the generation and about the processing part. There's also concepts of computer vision and image processing. Any ideas about the difference? These are two closely related fields.
Yeah, the image versus a graphic.
Image processing versus computer vision.
Oh, yeah.
So you can imagine with, what the names imply. The vision capability you can assign to a device or computer, right? So what does that mean? I mean, Which one do you think is higher level? Computer vision or image processing? So computer vision typically refers to what AI mostly deals with, what data science said, to understanding or making sense in some cases of images, or either recognizing them, detecting them first of all, recognizing sometimes relationships, interrelationships between objects, etc. But image processing typically refers to what you do as your first steps, like initial processing, low-level so-called processing, starting with the actual pixel values and looking at some low-level features, index, words, etc. And very typically, you start with those low-level features, even if you have a computer vision application in place, like recognizing objects. You typically start with these basic processing steps. Image processing deals with. So just to clarify these two concepts, and we also the idea of images versus graphics, as we did last time. So we saw this picture before, and we know the context of the image processing and computer vision fits within this larger realm of digital imagery, synthesizer, and natural, etc. So you deal with obviously with the social media and all you have to deal with all kinds of images, and depending on the image type and also the application or your goal, the way you process for both low level and high level processing for the ultimate goal of what your application is about and understanding the context would be different. So these are some typical examples. So you may also find this useful in maybe implementing working through the projects that you mentioned. So you may want to just try those algorithms or methods with different types of images. Obviously, for security applications, you have either still or obviously sequence or video recordings of security images. So you deal with different kinds of images, almost all of which will involve or require some kind of pre-processing, initial processing. And for the video data, where you have not just a single shot, but obviously a sequence of frames, you will also have so-called video segments or clips that may also contain different types of data. But in order to feed any kind of multimedia data into any processing system or information system, you would have to have some kind of a representation of your so-called signal, right? So that signal at a very simple level could be something like, radio signals or radio waves. But for image processing purposes, that signal would be a two-dimensional set of values from each coordinate, x and y. So it's going to be a two-dimensional function, just to get the mathematics straight. But then that signal, initially an analog signal. What do we mean by analog within the context of images? The optical color values, right? Mm-hmm. So our human vision system works pretty much like that, with a finite resolution anyway. So you would have to sample that, get a finite number of pixels, obviously, to work with. And what is quantization? So sampling is done at this spatial coordinates, spatial meaning in x and y coordinates, right, in the space coordinates. And quantization is the idea of digitizing the quantity or the level of, let's say, the color values. So for a color image, you capture 3 color values, maybe R, G, and B. So the quantized representation of these color values refers to this idea. And this has to do with the resolution, with color resolution, or the quality, eventual quality of the image too. Right? So you may know from most of the monitors, etc., TV representation. So this is also referred to as the color depth. Right? How many colors can you possibly represent with a number of digital bits? So if you're dealing with web design, graphics, etc., this is also for synthesization, synthesis purposes. This can be important. The more, obviously, colors you can represent, or the higher quantization level, the higher quality Higher quality meaning the closer you get to the real world representation, right? How many bits do you typically spend, let's say, on a monitor or display like this per pixel? Any ideas? If you go to monitor settings, for example, of any ordinary monitor, you can set the color depth, right? The color representation. So, have you ever paid attention to those?
I think not. Yeah. Yeah.
So very typically, the color depth or how many bits is used to represent one color level with the 3 dimensions will be in the order of 24 bits, 32 bits, or sometimes higher or lower.
Okay.
So 24 bits means 3 bytes per pixel. 3 because you have 3 color dimensions, and then you can imagine how many bytes it will take to represent an uncompressed image this way. 3 bytes per pixel. So if you're dealing with 2 million pixels, that gives you 3 megapixels anyway, right? 6 megabytes. That's 3 bytes per pixel, etc. So uncompressed images can take a lot of data. You can figure from this idea too. And that's why you need the next step to efficiently deal with digital images. We're talking about the imager signal, right? So if you already have 3 bytes per pixel, dealing with millions of pixels or megapixels, in order to make it more efficient, more realistic, to store, transmit, and process digital image data, you need better coding mechanisms. What does coding mean in this case? To represent all these bytes, now you're down to bytes, right? Zeros and ones. Without losing the perceptual quality, the actual content of the images, in terms of what the features that that are important, etc. What is the best coding mechanism? In other words, what's the most efficient way to represent your data? Any examples for a good image coding technology that's familiar? You already know that. Everybody knows this, but you may not realize that you know it. Right? Any acronyms that you can think of? JPEG, yeah. JPEG is one of the most successful coding mechanisms. What does coding mean? Everything is sampled and quantized for sure. But the way to code it, encode it, encoding and decoding, just the opposites of each other. To represent your zeros and ones after your quantization step can be a big challenge. JPEG does a good job because it can represent what is important in your data. It's a lossy compression mechanism to get to some of those details. But coding is the third important piece in the digital world, so you can make it a lot more, in fact, efficiently. So these are the 3 main steps in dealing with creating and then dealing with digital images. We talked about this briefly last time, and we'll get to this point next time also when we talk about audio and audio representation. But this is just a simplified one-dimensional analog signal sample at certain time intervals, typically equal time intervals. Right? So if this is the time dimension, you're sampling at certain time intervals. If this is a space dimension, then you're obviously sampling at equal spatial dimensions, equal spatial intervals. So each one of these, for example, could be for digital images. If this is the space domain, the XY direction, one of the XY dimensions. Each one of these could be one color value, one of the 3 color dimensions. If it's an audio signal, this could be one of the channels. If it's stereo, you have 2, right? If it's multi-channel, you may have 5, 6, etc. But regardless of the signal type, you need to have some kind of a sampling. So one of the ideas is, what's the ideal sampling rate, right? You don't want to oversample it too much, too many data points. And if you don't sample it at the high enough frequencies, then you run into other problems. So we'll discuss that when we're talking about audio and video next time. We will other examples. But the analog signal, this is the optical signal that your camera lens will receive. Sample and hold, sample signal in this case would mean a bunch of pixel values, color values. So this only represents, of course, part of the real world. But the trick is, in both sampling stages, quantization is more straightforward, but sampling and coding need to be with some tricky parameters, right? Mm-hmm. Efficient enough, and at the same time, sufficient enough, meaning to sufficiently represent the real world data without compromising, much. So JPEG, for example, can give you a compression rate. Have you ever wondered? What's the images that you take with your cameras? What's the number of megapixels, typical numbers? You can pretty much figure this out yourself. Let's say when you set your phones or other cameras, what's the megapixel levels you take?
The default, I think, is 12 megapixels.
12. It can be a bit higher depending on the. Let's go with 12, right? 12 megapixels. So if you take just a single shot of an image with 12 megapixels uncompressed, and let's go with the conservative number of 3 bytes per pixel, because with 24 bits color depth, that's what you would get. Some cameras will have higher. 3 bytes per pixel, 12 megapixels. How many megabytes would that give you for a single image? 36 already, right?
Yeah.
And what's the typical image size when you take an image? Few megabytes, right? Yeah. 3, 4, 5. It can vary, but never 30 at that megapixel. Right. That's what coding or JPEG coding gives you, at least 90% reduction. But when you compare an uncompressed and compressed image, there is hardly any difference that human eyes can detect. And that's the trick part of most coding mechanisms, which JPEG does a good job with, and MPEG and some other video coding mechanisms also give you very significant reductions, right? MP3s were used to be popular 10, 15 years ago. One of the main, success was because of this good coding, reducing the data rate without compromising quality, with so-called perceptual quality of data. So the sounds almost, not like perfectly, but almost like the original one. The images look much like the original, and the videos are noticeable also. So that's the idea with the coding or compression part. But images can be represented by a collection of pixels. Of course, each pixel can be represented by a color value, which can be as simple as a monochrome image. If it's not color, it's single dimensional, of course.
Right.
And monochrome images can be either grayscale, meaning one of the 3 dimensions only, or even binary images, which will be either just a black dot or white dots. If you have enough of those little pixels, the image may be okay, but it won't be as, of course, crisp or high quality as a grayscale or color images. So we talked about the 3 main steps: sampling, quantization, and coding. Just go through some examples. So you basically compartmentalize, right, your otherwise continuous image or almost continuous image to start with. So each area here will need to come up with some kind of a color value, right? So that's what your lenses or optical processing tries to do. So from multiple color values, you try to approximate that, maybe take an average, or there are some other smarter mechanisms, obviously, to also account for the interpixel relationships, not to treat every pixel independently, because there's a high level of correlation, obviously, between adjacent pixels, right? So optical processing and cameras try to be smart with that idea also, with their light sensors at every pixel area. there's some kind of an analog to digital conversion. So the sensors give you a single pixel value at the end. Those pixels can, at the very simplest level, can be binary pixels, 0 or 1. Of course, this gives you the highest level of efficiency, 1 bit per pixel rather than 24 or 32 bits, right? But the image quality can be very different. So the color depth can be important here. If you're talking about just one plane instead of 3, one dimension, you can have what's called a grayscale image. So if you are, for example, spending 8 bits, 8 binary bits for each gray, for each pixel, you may have how many different shades of gray with 8 bits?
Yeah.
Slightly more than 50, but you get 256.
Yeah.
250. How many gray levels can you have here? It's a trick question.
Yeah.
With 8 bits, what's the total number of possible values? 0 to 255. The number of possible values would be 256. How many gray shades? How many shades of gray?
Yes.
So in that spectrum, what does 0 and 255, what do they represent? You would need to go from pure white to pure black, or vice versa, right? So the extreme values would be black and white, and in between you would have 254 shades under this assumption of 8 bits. But this may also be a higher number of bits, 12, 16, etc. And if you are talking about 3 dimensions or 3 planes, there are different color models. RGB is a very typical one. It's also used in web design, graphics, etc. Other alternative 3-dimensional color models exist. So RGB. What's special about these colors? Anybody know? So you can imagine, there are more than 3 basic colors, right? Red, green, and blue are 3 of them. But what's special about them? Why not yellow or
pink or fuchsia?
I feel like with these 3 colors, you can derive multiple colors.
Yeah.
That's true. But what does make them maybe candidates, right, for that kind of a representation?
Mostly what we see comes under that.
Right. So have you guys ever bought paint for a paint shop? You go to the paint store, paint shop.
Mm-hmm.
They only have there are a few basic colors, right? Mm-hmm. Base colors. You pick up and you go to the counter, and from hundreds or thousands of different color shades, all kinds of colors from the spectrum, they can actually mix paint and give you the exact shade and color, correct?
Yeah.
Because there's no way they can store all kinds of possible colors. Yeah. So just like and they use some color components in mixing in those machines. Not exactly the same idea. They don't use RGB. It's a little different when you're mixing paint, because it's the opposite of actually the color space. The paints actually absorb certain wavelengths. They reflect the others, so it's kind of the opposite of this, but the idea is similar. With 3 independent color dimensions, you can represent not all, but most of the colors in the visible spectrum, color spectrum. And RGB happen to be, this is an optical feature with respect to the human vision system. These 3 dimensions are almost orthogonal, meaning they're independent. Not perfectly, but close enough. Yeah. So any combination of RGB values can represent a great majority of the visible spectrum, color spectrum that we can actually see with the human vision system. So it's the best and almost perfect representation with 3 independent color dimensions with RGB values. But of course, these can be represented different dimensions too. Do we have PowerPoint here? I think we do.
Yeah, yes, we do. I think all you have to do is on, if you wanted to, I think,
So if we have any PowerPoint. So I would like to just demonstrate that.
Oh, yeah, yeah.
Yes.
I know we can find it. One second
We
here.
just
I think I can.
Start.
A search, yeah. Sometimes we can just do, well, there they've got the paint. Let me just do, oh, yeah, there we go. I will just,
Yeah, just a
There we
blank
go.
document is fine.
yeah, we'll just do the blank. Yep, we're good.
Shared on the screen.
And it's shared on the
Yeah,
screen.
great. Okay. So on any application, in fact, when you try to do a color selection, you may have seen this. You are given this option to choose the color model,
Yeah.
right? And obviously, what you see here is just the visual spectrum. And every color point here is a combination of some RGB values in the bottom. You may have used or seen this. And what you see in the bottom, of course, is the hexadecimal representation,
Yeah.
right? 3 dimensions. The first 2 digits are R values, 94. This is not 94. Why do we call it 94? So I know we read high here, it's hard to see. But 94 is a hexadecimal number, right? 9 times 16 plus 4, that's what it is. So the second 2 digits will be the G component, green. E0, in this case, E0 is a hexadecimal number again. And then AD is the B component, the blue. But you can also choose a second color model here. This is just PowerPoint tool because these are the 2 common color models, RGB and HSL.
Mm-hmm.
What does HSL mean? I don't think anybody is old enough to remember the old analog TVs here, the black and white TVs. They would have some dials in the back, the old analog devices, showing these dimensions. Even old black and white TVs they would have saturation, hue adjustment, and luminance, right? Brightness.
Yes.
So these HSL are the 3 color components that represent the optical or physical features of color values. They're a little better than the RGB. So if you choose HSL here, you can see the HSL values, hue, saturation, and luminance. Luminance is the brightness. So you can separate the physical property of luminance or the brightness as the 3rd dimension. And then H and S would just represent the color
Interesting, yeah.
components independent of the brightness level. Right? So HSL is actually a better physical model representing the optical features of the brightness and the 2 color dimensions, the saturation, color saturation, and the hue values. But any color can be represented by either an RGB or HSL combination. And there are other models too, but they'll all be 3-dimensional, similar to RGB and HSL. So you have 3 independent color values. So in a simple tool like this, even you can choose this RGB combinations or HSL combinations and get a specific color ranging from infrared to ultraviolet, right? So this is most of the visible color spectrum in the RGB space. So whether it's RGB, switch over, we already here, okay. Whether it's RGB or some other color model. So you have these 3 values at certain quantization or precision levels. So you end up with the representation, your digital image as a matrix of values, right? RGB, HSL, whatever they may be, column and rows. And the value could be either a gray level or some kind of a color or 3-dimensional color level, or even simply just the 2 possible values of 0s and 1s. But regardless, a digital image now is a two-dimensional function. And then you can do some basic processing with them, including segmentation. This is how a binary image would look like, the binary version of that color image. You obviously get much less detail, right? But this can be, you can imagine, 50 times more efficient, even without any compressing or coding mechanisms. So you have this image function, lowercase f. For the grayscale images, this can, of course, the range can be between 0 and some value. This is the example for the grayscale. You can probably argue significantly better looking than the binary version. And the color images will have these three components, possibly red, green, and blue, red, blue, and RGB values, or HSL, or some other color model. And obviously, this is a much closer representation of what this image was actually. It was about the real world image that this digital image is supposed to represent. So in the projects, you would also just work with some kind of a two-dimensional image representation that may represent some type of an image, like this example shows. These examples may represent. So it's up to you what kind of an image you start and use with, work with in your projects. So YUV is, for example, another color model similar to HSI or HSL. And that will also separate the luminance or the brightness from this. So with 24 bits, and this would be easy to figure out, right? 2 to the power 24 would give you 16.
Wow.
0.7 different colors in that RGB space, which in many cases is more than enough, but in advanced graphics, movie industry, obviously, the color depth, the number of colors can be a bit higher than this. So with 10 bits, you can get a few more shades of gray. And this is just a matter of mathematics now, how many bits you use. So once you digitize your image in raw format, the next step is to encode it, right? Some kind of it. Now you're dealing with just binary numbers. So you can go from your raw images, raw representation of just pixel color values to different formats, coding, and you'll end up with different file sizes, first of all, different quality levels. And some of these coding mechanisms will be lossy, some will be lossless, right? When you zip your folders, so you can reduce the file size for emailing, etc. You compress your data, correct?
Yeah.
It could be a Word document, PDF, or whatever. Is that a lossy compression, do you think, or lossless? When you use something like zip or other mechanism. So when you recover your data at the other end after emailing, do you expect only half your document or the entire document back? Lossless.
Yeah.
It's a good guess because you don't want to lose some of your pages, right? So you want to make sure you recover. So that's lossless compression, and it's clear. For numbers, documents, etc., you don't want to compromise any data. But when it comes to digital material, audio, video, images, you can afford to lose part of your data. And in fact, you do want to afford to lose, right? Why? Because the data representation after sampling is typically redundant. Meaning you actually represent, you capture more data than your eyes, or your ears can hear, or your eyes can capture. So this is called perceptual coding. Many of these compression schemes will use this. And it has to do with the features of human auditor and vision systems. Because we cannot hear two different sounds with frequencies that are too close to each other. This has to do with the audio, and likewise, the certain details at certain frequencies, again, if they're too close to each other, we cannot distinguish the two. So in the frequency domain, when you sample your data also at the frequency domain and get rid of some of the data that you cannot hear or see anywhere, you hardly notice the difference. That's why JPEG images actually capture the world with much less data. They're lossless, lossy compression. There's lossless dimensions in all of these, but the lossy part is what gives you the best data reduction. A JPEG image can be 1/10 or less the original size, thanks to this idea. An MP3 audio can also sound almost like the original audio, but with much less data, etc. And some other image formats also have compression ideas or coding mechanisms that can make the idea a bit more efficient. So we talked about some of this math, how many bits can be and bytes, etc. can be in a typical. So even in a very low res image like this, which is not even very practical nowadays, you can already get to 1.5 megabytes. And for most of the images today, if you were not using in compression, you would be in big trouble. So that has to do with, again, the three components of being able to even capture and store images. But there's a lot more than just capturing and storing that you want to do with images, right? So you want to move on to the next step and actually develop some kind of understanding, especially with all the data science and AI work that is being possible today. You want to include your images or other media data as part of these applications. You want to process the images further, much more than just being able to represent the data in digital form or encoding or for transmitting, etc. So this can involve some examples I mentioned here. So dating back to some early days of digital imagery, but you can basically extract the features, not just all the features, but moving on to the higher level features, extract, represent, and make available certain features. This could be simply for purposes like OCR, object character recognition, to convert your images into actual text representation. To all kinds of other security or other areas. So we've seen, of course, a significant growth and advances in this area, which basically evolved into solving a lot of problems. Like face recognition was a big disappointment. 15 years ago, after 9/11 and all of that, there was huge expectations, which did not deliver at the time. It was maybe too early, but nowadays that's almost a given, right? So you see face recognition being used very successfully as an example application, and all kinds of other image understanding and processing applications are in place. So we talked about some of these formats used in these successful applications also. So just to look at the bigger picture a little bit, what is involved in processing and understanding an image, starting with the raw image data, developing a knowledge base, and obtaining a result. This result will depend on what your goal is, obviously, what you're trying to achieve. If it's, for example, a face recognition or object detection recognition example application, you will be trying to recognize or identify the faces in your database, and that will involve the representation and description of the prominent features that may show the result of either pre-processing or some kind of segmentation. So we are going to see some examples on some of these basic processing steps or aspects of image processing, which may be performed either in the spatial domain or frequency domain, right? Which can be equivalent to each other. So there's the corresponding frequency domain methods. Maybe you're familiar with this if you've done any signal processing work or spatial. What do we mean by this? In spatial domain, you're dealing with, let's say, the color values directly in your space dimension. X and Y, these are your coordinates that you're working with. Basically, your physical, actual data, right? And in frequency domain, and there's a one-to-one correspondence, so you can go from spatial domain to frequency to spatial, right? So whatever you do here, you're also doing the equivalent in the spatial. So we're talking about the single data, just like two different color models can be used to represent the exact same color values. The exact same image or signal can be represented in two equivalent ways, frequency or space. But why do we have these two domains? Because certain operations are easier and in fact more effective, either in space or frequency domains. Most of the filtering or other operations are typically done more efficiently and more effectively in the frequency domain. That's why we go through the trouble of moving to frequency. So what do we mean by frequency domain? For example, low frequency components of audio. Which are those? When you do the audio settings in your car stereo or your car audio system or any audio system, right? So you get an equalizer. What are the three components? You get the high pitch, like medium and the bass. What are those? Low frequency components of your audio signal, medium and high frequency, right? So when you adjust those, you can imagine the effects on the audio.
Yeah.
You can relate to the physical properties of your audio, right? Same thing even for the images. What are the low frequency components in an image? You can capture and target those obviously much easier in your frequency domain operations. So if you need to blur the images, you reduce the sharpness, you would reduce the low frequency components, right? Or you reduce the high frequency components, so you can reduce the sharpness, make it less sharp, make it more blurred, the overall. So if you're just, for example, changing the high frequency components, this will affect your entire image, not just a portion of your image. So your entire two-dimensional image is represented at each frequency component. So you, in a maybe batch mode, you can target all high frequency, low frequency, or medium frequency, etc. components of your entire image from a single value of point. Left and right balance B. So in the analogy in the car audio system, left and right balance, this is a little different. So because in stereo audio, left and right are supposed to be independent channels, right? So or slightly independent. If that's the case, then you're just dealing with two different streams. The two streams being equivalent. Most stereo systems are not perfectly independent, so that's a kind of questionable distinction. But the stereo or even multi-channel audio simply, typically, or ideally is just a collection of multiple streams of audio. So that's a good question, but it's a slightly different concept. So you can operate either in space or frequency domains, and things like filtering, changing the sharpness, the color adjustments, and most importantly, for the purposes of coding and efficient compression, operating in frequency domain is almost a necessity. Like JPEG compression, MPEG compression, audio compression works all in the frequency domain. Why? Because we want to eliminate the frequencies that we don't hear anyway. That's much easier. In fact, that's only possible in the frequency domain than working in space domain. So concepts like Fourier transformation, digital signal processing techniques are heavily used in both audio and image processing. If you're not too familiar with those mathematical concepts, that's fine. But it's enough to know that working in the frequency domain, high, low frequency components, can actually serve a lot of purposes, including multimedia coding and obviously decoding going back. Another interesting feature that you can use, and this is also in one of the projects, is the overall features, not just in the frequency domain, but even in the spatial domain, like what you may call a histogram. This is a simplified representation. What you see a simple image on the left, right? So many image representation, image querying, image searching, multimedia applications. It can use what is called a histogram, which is a simplified representation of the prominent color features. This is a grayscale image, just to make it simpler. In a color image, you would have 3 different histograms, right? RGB separate ones. But in grayscale, what you see here on the right-hand side is different levels of gray. And the histogram, as the name suggests, is how much of each color component you have in the totality of the image, right? So, for example, the first one, if that's just pure white, you have so many white pixels. The next level of grays, you have so many. So this distribution gives you a one-dimensional, reduced dimension, simplified representation of your image, right? So another image similar to this would have a different histogram distribution. And this can give you both a simple representation and also a capture of the general color-based representation, which may, in some cases, will give a more human-like description or representation of the image. So when we perceive an image of a scenery, etc., a lot of when you're asked as a human to come up with the images that are similar to that, we often, as the research suggests, use in the back of our minds. Obviously, we don't think of numbers, but the way our perceptual system works will have some kind of a histogram-based representation, so that when humans are asked to come up with similar figures, they will actually match very closely what the color histograms or image histograms will do. I would like to show you an example for this as well. I'm sure some of you have used or seen, but many may not have realized that this Google opening page, actually has a search by image option, right? Where you would provide an image rather than keywords to look for. So that's this image-based search. We often use techniques based on color histograms. So let's just find
just click on image.
let's just go look for a tree image first, just any tree image. Right? I'll just download this. Hopefully there is no.
It's fair use. Yeah. Yes. Save image. 3 more down. Save image as.
Save images.
Yeah. You just put it.
So let's just put this temporarily somewhere local, right? So I have an image to search with. So you click on search by image, upload a file, and this is the image that I just downloaded anyway. So let's just give it the same image, search for it. Obviously in exact matches, you find the exact match, but visual matches will look for visually similar matches, right? So you have the image itself, obviously, and then many other similar 3 images, right?
Yeah.
So how an algorithm like this, like Google uses, can look for similar sets of images. So color histograms, when you look at the color histogram representation of these images, which would be part of your job, would actually have a higher degree of similarity with the image that you're searching for. So you're trying to match the human perception or human description
Yeah.
of images with features like color histogram. So that's one of such dimensions to be.
And I don't know if you have a minute. There's another Google fun little tool for the students to play with in that area. Let me just.
Go ahead.
Yeah. And if you go under, guys, if you go under for working with images, by the way, Dr. Dactus was talking about computer vision. And so if you'd like to have a little bit more about, seeing like a machine, this is a very nice overview of some of the topics that Dr. Dactus has covered. So this is a nice reinforcement. But it's down here, the Google Cloud Vision. This is kind of fun here. What you can do is sort of the same thing. You can, let me just see if I can just make this a little bit more. Let me just browse and let's just see. Let me just open this up. And hopefully, and you have to say I'm not a robot. But this is really interesting. What you can get now with these APIs is it's actually trying to give you a layout of what it thinks is in that image, and it's kind of identifying. But here's trying to look at that. You can see the different RGBs just to see what it found as the dominant colors. And it's even, nowadays, they're even trying to attach metadata, meaning it's very unlikely that this is, rated for adults. It's very unlikely it's a spoof. It's unlikely that it's something medical.
Location.
Violence, racy. But it's quite interesting what some of these APIs are doing. And at one time it had kind of a histogram, but now it's gone to, this color, breaking it down so you can see what the dominant colors are in the image.
Yeah, thank you. So many of the AI techniques. This is not.
And if you want to, if you go to the download file.
Trying to get the.
Yeah, there you go. Very good.
Whether you're using your representation for a searching retrieval mechanism or some other data science application, or simply for enhancing color or visual quality, the color histograms can be quite useful and very efficient. You can see certain colors have been eliminated from the left-hand side version, so it's a darker color now, with the bright colors being eliminated. So you can also make a more efficient representation of the image. So you can see certain colors have been eliminated again, so you can reduce the file size, but without having to compromise the image quality or precision very much. These operators, what you do on your image data, the two-dimensional functions, can be linear or non-linear operations. So that's a little bit kind of beyond our scope, but this can basically allow you to apply some common operations like high pass and low pass filters, which is exactly the example that I gave with your cars, or any audio system.
Yeah.
Right? So in the image world, you can also apply these so-called high pass and low pass filters, meaning pass the high frequency or low frequency components more. So you reduce the size, you can improve the perception or the quality, or you can adjust certain features, make your images less or more sharp, or the nonlinear operations that work on certain specific aspects like certain pixels, threshold, certain levels, either amplitude or frequency domain. But the result can be some visual processing applications like smoothing your image through some kind of low pass filters. Some of these examples are in actually example projects. So the end result from your linear operation, whether you operate in spatial or frequency domain, may be smoothing. Some examples are mentioned here, also in the project, like Gaussian filters, targeting certain frequencies. So if you are operating in the space domain, meaning pixels and pixel values surrounding, you'll basically take into account some neighboring pixels.
Yeah.
And your window of operation may be of different sizes. An example is mentioned here, 7 by 7, meaning for a total of 49 pixels would be involved in the computation of every pixel value. And there is a frequency domain equivalent of every spatial domain operator. But again, we won't get into all the details of these processing techniques, but rather just let's mention a few of these application areas. Edge detection. Why is this important? The objects can be at a high level, description levels can be best and efficiently described through their edges, right? In fact, and these are in line with also the human psychology and perception, etc. A lot of times we recognize objects with their edges. So the areas with the same similar colors are often ignored, and you perceive and interpret the shapes or objects based on their edges. So you don't often care how big a ball is, as long as it's a round figure, meaning its edge is actually a circle or almost a circle. That's a ball, right?
Yeah.
A small ball or a large ball makes little difference to our perception. So edges are the most important part of an image in terms of human perception. And some techniques to represent the regions or shapes involve region growing or image warping examples. So some technical details are provided here, so we may not have time today to go through all this, but we are going to complete this discussion on Thursday.
Yep.
And move on to audio processing with similar discussions in one-dimensional, simpler, obviously, domain, but video will, of course, expand this. So in the visual domain, you're going from two-dimensional images to three-dimensional, including the third time dimension, plus the audio track, which puts together all these features, both visual and audio features together. So we will complete this discussion within the context of images, as well as adding the audio and video dimensions to that. Wrap this up, and we should hopefully have some time also on Thursday to go through some of the example projects which you can choose and put some of these ideas into practice and see for yourself how things work in the image domain, two-dimensional space, audio domain with one dimension or multiple one dimensions, obviously with stereo or multiple channels, and of course video data, which will be slightly more complicated but will involve similar techniques and approaches. Any questions, suggestions, or ideas before we wrap up for the day?
And these are all areas to think about. Again, if you're, even if you just want to get in at a very rudimentary level, but the video analytics is a growing area because, we have drone footage, we have all this camera footage, and it's too much for people to make sense of. So, we talk about, well, how does a computer, see an image? Well, how does it interpret a video? Because now you have to add that temporal quality.
We have a lot more data and a lot more ways now that we can deal with data. When I was a graduate student, I did my PhD work in video databases, which was a fantasy back then in the late 90s.
Yeah.
I mean, you would need a big, server and big workstation, even to do some basic processing to what, we're talking about. Nowadays, your phones can do, what the servers back then could do.
Yeah.
So you have obviously more storage, more processing,
Yeah.
more transmission capabilities, in addition to a lot more digital data, right? So we're only using very little of what we can and should with the data and images, etc. So the AI field and data science field is expected to see a lot of growth when it comes to multimedia data as well. So similar to the successes of NLPs and ChatGPTs, etc., that deal with text and numeric data, etc. In the next decade or two, we may see similar advancements with multimedia data involved. So
interesting applications like video sports analytics is a growing area. The idea that in the future, it's great if you could have a coach, but if you can't afford a coach, what if you could have someone just film you playing tennis and then have it analyze your footage and give you recommendations? Oh, you're doing this with your backhand, you're doing this with your forehand, basically giving you coaching on how to improve your game.
Sports broadcasters and coaches use ideas like this already a lot. So in my, in fact, presentation when I interviewed for this job 20 plus years ago, I did make one of those presentations. But again, the technology has come a very long way since then, and we are expected to see more growth in the area. All right, thanks for being part of this discussion. We'll see you guys again on Thursday.
Yeah, was there a question online? We can get that question.
I actually just responded to a comment thinking it was me, but
I did it
on your behalf.
Oh, yes.
All right.
Yes. And I think that is so interesting. I'd be curious to see how they did the eye analysis to test and figure out that as human beings, it's edges that really, for us, help us. Yeah. Because, when we see things, our brains just see it. And
we simplify things without even
realizing how is our brain processing regions and processing, looking for edges. And I also found that very interesting. You had a slide on the fact that not all colors are the same, that there's certain colors we focus more on. Same thing, like dogs are very green, yes. Yes. In animals, they see green is their most sensitive. Yeah. Very interesting.
Well, actually, I assumed they were colorblind for a long time. And it turned out they actually see some colors.
They do, yes,
They're not just colorblind, but they just perceive it differently.
Yeah. All right. So, so we'll see everybody again on Thursday.